All right, so this is what the week one schedule is going to look like. This is the welcome right now. Hi, I'm Olivia. I'm actually giving your first lecture in just a few minutes as well. I'm going to be talking about the foundations of quantum mechanics and the history of those first 100 years and connecting it to what we are doing now and how we are using quantum phenomena to make quantum computing better. And then I will join you again shortly after that for a live Q&A. So if you have any questions for me and my journey or about my lecture, please direct it there and I will see you then. And then we'll have our first lab at the end of the day as well, which is really exciting. So we'll be able to actually recreate some famous experiments that I talk about in my lecture at home with Qiskit, and you guys will all get a chance to do that. Then later in the week, we are going to have some really interesting lectures on some quantum algorithms. We're going to look into quantum simulation, foundational quantum algorithms, and then we're going to look towards the end of the week and we'll talk about the physical realization of qubits and the evolution of hardware. And then we'll talk about some practical quantum algorithms of the modern day as well. Going to week two, which is next week, we will have some benchmarking lectures and some error detection and space-time code lectures with some great Q&As as well. And then we're going to start talking about how we do accurate quantum computing in the utility era, which is the era that we say we're in right now, when we have over 100 qubits and we're trying to figure out actually how to make the best use of them possible. And we have some great experimentalists from IBM who are going to give us lectures and deliver some Q&A on that. And then very end of the week, we're going to have our panels. So the first panel, which will really just celebrate your graduation from the Qiskit Summer School and try to help you sort of figure out your next steps. That's going to be a career in quantum computing panel moderated by Qiskit. So we get a ton of questions throughout the week on how do I take the next step? How do I build my career in quantum computing? This is really the best place to direct those questions. So if you have any that are not about the lectures that you are watching during the Q&A, but you still want to ask the lecturers or some of the panelists how they got started, what was their journey like, that is the best place for that. And then the very last panel that I will be back to moderate again is the future of quantum computing, where we are going to talk about where we go from here and what the future is going to look like to the best of our ability, and try and make some predictions for what we think the next 100 years, well, I don't know if we'll go that far, but the next, tens of years are going to look like in the field. And we have some really, really great panelists who are going to share their expert insights with me and with all of you. And of course, we are open to questions. So if you have any throughout the week, please direct them in the Discord and I'll start collecting them as well. All right, so we're going to wrap up here because my lecture is going to start in just a few minutes, but I just wanted to take a moment to thank everybody. This is really a monumental effort from so many people to try to make this happen and make this the best possible educational experience for you guys. So it's not just me, not just Junior. We have so many people, both on the IBM side and externally, who are on board, who really care and want to support this mission. And I just wanted to take a moment to thank them and make sure that at least their faces are recognized. Yes, and this is the internal team as well. We have people who are forward facing, Junior and I, and then we also have a lot of people who are working behind the scenes as well, like the video squad, the people writing the labs, the events team. So big round of applause, big thank you to them. None of this would be possible without their help. And as you can see, this is a huge investment for all of us. And I hope for all of you as well, because you really get the most that you put into this school, or you get the most out of it that you put into it. So I don't know if Junior already said this, but you get the most possible educational experience if you do the labs, if you participate in Discord, if you're actually running the experiments alongside us. Don't just be a passive learner. Don't just watch the videos, but contribute as much as possible. And we think you'll really get a big benefit out of this event. All right, that's my spiel. Thanks, Junior.
Okay, that's great. Thank you, everyone, and we can move on to the first lecture by Olivia, starting in
We'll
5
see you
minutes.
then.
Hi, and welcome to the first lecture of the Qiskit Global Summer School. I am honored to be able to deliver the first lecture in a series of 2 weeks of lectures from IBM contributors. My lecture today is going to focus on the foundations of quantum mechanics. We're going to talk about the history of quantum mechanics, how it came to be, how it was discovered, who discovered it, and when. And then we're going to sort of gently merge into the future and talk a little bit about where this field is going. My name is Olivia Lanes. I'm the global lead for education and learning here at IBM. And let's get started. So in the beginning, in the pre-quantum era, classical physics reigned supreme. Scientists confidently relied on the foundations laid by Newtonian mechanics, Maxwell's electromagnetism, and believed that these theories could describe the universe completely. Newtonian mechanics, illustrated by simple systems such as inclined planes and pulleys, successfully explained everyday motions and forces. Objects followed predictable trajectories governed by clear laws. Similarly, Maxwell's equations elegantly unified electricity, magnetism, and optics. Phenomena like electromagnetic waves propagating through space seemed thoroughly understood. Yet, by the late 19th century, some scientists famously declared, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." A pretty unmotivating statement overall. However, this confidence overlooked subtle anomalies at atomic scales, problems that classical physics couldn't explain. These unresolved mysteries would soon open the door to quantum mechanics, revolutionizing physics forever. Let's explore some of these first anomalies. As is often the case in science, the most exciting discoveries begin to happen when nature stops behaving the way you expect. Seemingly wrong experimental results give way to deeper exploration and understanding. One such example of that is the very cool-sounding ultraviolet catastrophe circa the 1900s. From classical thermodynamics and electromagnetism, Lord Rayleigh and James Jeans derived a formula that predicted just how much radiation black bodies of different wavelengths would give off, where here I is the intensity, lambda the wavelength, T the temperature, K is the Boltzmann constant. Now this formula worked really very well, except for when lambda went to 0, wavelengths in the ultraviolet range. The intensity was predicted to go to infinity. This implies that a black body would emit infinite energy at high frequencies, and obviously that's not what experiments showed. Experiments showed that radiation intensity increases with a frequency up to a peak, and then it drops off at shorter wavelengths, the ultraviolet and beyond. So the classical model matched at long wavelengths, but failed dramatically at short ones. Then Max Planck came along, and he tried to force-fit theory to experiment and stumbled upon a radical idea. Energy is not continuous. It's emitted in discrete packets, or quanta, and he introduced this formula shown here, E equals h nu, where E is the energy of a quanta, nu is the frequency of the radiation, and h is Planck's constant, which is a new fundamental constant. Now at the time, Planck didn't really assume that this had any deeper meaning. He just found a way to make the equation work and assumed it was, a cool little math trick. And even the best physicists do this at times. But as hindsight is always 20/20, we now know that this was really our first glimpse into quantum mechanics and using it to make much more accurate predictions about the world. Now let's move on to another extremely famous experiment called the photoelectric effect. The photoelectric effect is the phenomenon where light shining on a metal surface causes electrons to be ejected from that surface. This was first observed in the late 19th century and systematically studied by Hertz in 1887 and later Philip Leonard in 1902. Under classical wave theory of light, here's what physicists expected to happen. First, that light intensity, or the brightness, should control how much energy electrons gain. 2, there would be a delay. Electrons would gradually soak up the energy and then eventually be ejected. And 3, there would be no threshold frequency. Even low-frequency light, if it was intense enough, should eventually cause the electrons to be ejected. So in short, brighter light equals more energy, regardless of the frequency. However, experiments showed the exact opposite. Electrons were ejected instantly, no matter how dim the light was. The ejection only happened if the light's frequency was above a certain threshold, and increasing intensity at low frequencies did nothing. Lastly, increasing the frequency, not the intensity, increased the electron's energy. This could not be explained by classical wave theory. So, that's when Einstein stepped in. You've probably heard of him. Einstein proposed a radical idea, that light isn't just a wave, it comes in particles called photons, each with energy proportional to its frequency. Remember this equation from a few slides ago. He suggested that one photon hits one electron. If the photon's energy is greater than the work function phi, the energy needed to liberate an electron from the metal, then the electron is then ejected. Any extra energy becomes kinetic energy for the electron. He came up with the photoelectric equation shown here. K max equals h nu minus phi. K max is the kinetic energy of the ejected electron by the work function of the metal, and then h and nu we've already defined previously. So looking for experimental confirmation of the theory, that happened in 1914 by Robert Millikan, who initially tried to disprove it, but instead ended up providing the strongest evidence in its favor to date. The kinetic energy of the electrons increased linearly with frequency, not intensity, and the slope of that line was measured experimentally to be Planck's constant, measurable and consistent. Einstein actually won the Nobel Prize for this work in physics in 1921, not for relativity, as many people think, but for explaining the photoelectric effect. So in the end, a lot of people like to say Einstein hated quantum mechanics, and maybe there's still some truth to that, but he also had a really big hand in shaping it as well. Now let's keep going, staying in chronological order. In the early 20th century, the classical models of the atom, like the Rutherford model, couldn't explain why atoms were stable or why they emitted light at only specific wavelengths, like those seen in hydrogen spectrum, for instance. And yet, scientists were seeing it again and again, the exact same wavelengths. Taking hydrogen as an example, they saw that light was only emitted at very specific wavelengths, like the ones listed here. They just didn't know why. And then Niels Bohr came in, and he said only certain discrete or quantized orbits allowed for electrons. His key postulates were that electrons orbit the nucleus in specific energy levels, or shells, without radiating energy, unlike classical theory, which would have predicted that the electrons spiraling into the nucleus would be always emitting energy. Energy is only absorbed or emitted when an electron jumps between these levels, as crudely shown by this diagram here with these different colors. The energy of the emitted or absorbed photon corresponds to the difference in energy between the different levels. So here, the energy of the photon would be En minus Em, and that equals h nu, where En and Em are the energies of the different levels, which we can label as 3, 4, 5, 6, and so on. His theory ended up predicting what we kept observing for hydrogen really, really well. However, there were a few issues. For one, it only worked well for hydrogen, which has a single electron, so maybe that's not so surprising. But it couldn't explain the fine structure or the electronic spin. We ended up finding the reasons for this even later on. Now, coming off of the success of that experiment, de Broglie proposed a somewhat radical idea at the time, that if light can behave like a particle, then particles, like electrons, should be able to behave like waves. de Broglie proposed that any moving particle has an associated wavelength given by lambda equals h over p, where lambda is the de Broglie wavelength, h is Planck's constant, and p is the momentum of the particle, just m times v for non-relativistic speeds. This means that faster moving particles have shorter wavelengths. Heavier particles also have smaller wavelengths. But for macroscopic objects like a baseball, lambda is incredibly small and undetectable. That's why we never see baseballs exhibiting wave-like properties, for instance. But for tiny particles like electrons, the wavelength is measurable and it matters. The de Broglie hypothesis was spectacularly confirmed by the Davison-Germer experiment, and this experiment was as follows. Electrons were fired at a nickel crystal and then scattered. The scattered electrons created interference patterns that were measured with a detector, just like waves diffracting through a grating. And from this, they were able to conclude that electrons were behaving like waves, not just like particles. And this was a turning point. It validated the idea that matter has wave-like properties and helped usher in the formal development of quantum mechanics. Before this, particles were thought of as little solid objects. But because of de Broglie's idea and its confirmation, they showed that electrons and all particles, really, can exhibit interference and diffraction, which are inherently wave-like phenomena. And that the wave associated with a particle is not a physical ripple in space, but rather a probability wave, which is the central idea that was formed later in the Schrödinger formulation. Now, this is when quantum mechanics sort of faced a turning point. In 1925, Heisenberg introduced what we call matrix mechanics. This was the first complete and consistent mathematical formulation of quantum theory. What Heisenberg proposed was radical at the time. Instead of trying to track particles through space like in classical physics and measure their trajectory at different points, he suggested using matrices. Yes, those things from linear algebra, to represent observable quantities like position and momentum. One of the key insights here is that in this formulation, position and momentum don't commute. That is, when written as matrices, x times p does not equal the same as p times x. Instead, they follow this commutation relation, where those two square brackets indicate a commutation relation, and for x and p, that equals I h bar. Now, a commutation relationship is defined as two operators, a times b minus b times a. If it is 0, we say that the operators commute, and they can be observed precisely simultaneously. But if they don't, well, it gets a little bit more complicated. And this isn't just some quirky mathematical fact. It's deeply tied into the uncertainty principle. It tells us that we can't precisely know both the position and momentum of an object at the same time, which is a sharp break from classical thinking. You can visualize this in part with the figure on the right. Each row in the image represents a different quantum state. The left plots in red show the uncertainty in the particle's position, and the right plots in blue show the same for momentum. Basically, how many possible different values there are for momentum in the position the particle could occupy. At the top, momentum is shown very precisely, and we can be extremely confident when we measure its value because the peak is so narrow. But for position, for the same measurement, the spread is quite large, and we can't isolate exactly where the particle is located. And then the opposite is true for the bottom images. When we know exactly where the particle is, we can't precisely measure the momentum. These diagrams show that both of these non-commuting operators, position and momentum, cannot be measured definitively at the same time. When we're sure of position, we are unsure of momentum, and the opposite is true as well. Heisenberg also gave us this eloquent equation of motion, rightly named the Heisenberg equation of motion, which is shown here, where A is an observable that we can measure, like position or momentum. Now, this is revolutionary because it replaced Newton's equations with something operator-based, again emphasizing that quantum theory is about how observables evolve in time, not about particles following a specific path. Now, just a year later, Erwin Schrödinger introduced wave mechanics, where particles are described by something called wave functions, usually written as psi of x or psi x and t, if dependent on time. This is actually what's being plotted on the previous slide. A wave function psi is a mathematical function that describes a quantum system's state. It encodes everything that we can know about a particle, like an electron or a system of particles. At its core, the wave function tells us the amplitude for finding a particle at a position x. But because the wave function is a complex valued function, meaning it can contain imaginary numbers, it's not directly observable. What we can observe is actually the probability, which is the modulus of psi of x squared. That's the probability density of finding the particle at a position x. Now, Schrödinger's equations looked very different, but strangely, the results agreed with Heisenberg's. So the big realization here was that both matrix mechanics and wave mechanics were mathematically equivalent. They're just two different mathematical representations of the same theory. Now, at this point, I actually want to take a short break from our history lesson and talk about the first key component of quantum phenomena that makes quantum mechanics so unusual, and that's the principle of superposition. Now, Heisenberg didn't explicitly talk about superposition, but his use of matrices to describe transitions between energy states involved adding contributions from different states. For instance, a rule that we learn in linear algebra that applies here is that if psi1 and psi2 are both solutions to this equation, in this case the Schrödinger equation, then their sum is also a solution. He sort of made note of this in his work and mentioned mixed wave states, but the implications of this weren't really examined until a bit later. Now, I want to discuss the principle of superposition with one of my favorite experiments as an illustrated example, the double slit experiment. The first double slit experiment was actually done over a century before, but it was a classical physics experiment done with light. The experiment was done much later with electrons. So for those who may not be familiar with this iconic experiment, the setup is this. There exists a source of particles. Here I've just created this purple box, and for all intents and purposes, it's capable of sending out one particle at a time. There's also a film in the path of the particles with two holes cut in it. The sizes are created and adjusted so that it's physically possible for the particle to pass through either hole and then be measured by a detector or a screen on the other side so you can visually see which hole the particle went through, allegedly. So during the experiment, what has to happen is this. First, one hole in the film is blocked off somehow so that the particle really has no choice but to go through the other hole. I've shown here only the particles that make it through the second hole, but if there were more particles streaming out of it, they would just get blocked at the first. So they make their way through the other hole, and then they would form a normal distribution on the measurement screen. And this makes good intuitive sense. And then we do the same thing with the other hole. We block off the second and let particles fly free, and some will make it through the first hole. And we would also see a normal distribution where the width of the distribution just corresponds to how large the hole is. Nothing weird happens until we open up both slits at the same time. What everyone at that time expected to see was just the two distributions at the same time instead of one. One for each slit, but still localized and still centered between the holes. Maybe they would have, a little overlap here. But that's not at all what was seen. What was actually seen and I apologize for my crude hand-drawn but fairly accurate squiggle here, is an interference pattern with many troughs and peaks centered about the middle of the slit, where there actually wasn't even a direct path for the particles to go through. Now, how could this be? How does this make any sense? Indeed, it is not obvious or intuitive how to interpret this. Well, probably to no one's surprise, the only way to do this accurately is through the lens of quantum mechanics, specifically hitting our first key quantum principle, superposition. If we were to write the mathematical expression, the wave function, that represents what's going on here in the picture, we would say that the wave function is equal to 1 over root 2 of the left hole plus the right hole. To calculate the probabilities, we would have to square the whole wave function, take the modulus, which would give us a value of 1/2 for each possibility, meaning they are equally likely and the superposition is even. The particle would then have a 50-50% chance to go through each hole. However, since both are solutions, the linear combination of both possibilities is actually also a solution. So in the end, there's no other option but to say that the particle actually somehow went through both holes at the same time. And this is an image of what we would actually see in reality if we measured it in a lab. One other interesting aspect to note here is that the interference pattern that appears on the measurement screen is only visible when we don't track which path the particle actually took. If you follow actual particles' trajectory with your eyes, or if it's even just possible to calculate it mathematically and backtrack it, then the interference pattern literally disappears, and we see the original predicted shape of the two distributions, which is wild, right? This is a great example of what people refer to as the measurement problem in quantum mechanics, but neither you nor I are going to be able to solve that one right now. Now, another key quantum phenomena that arises from superposition in the same experiment is quantum interference, which is basically the idea that these particles don't behave like tiny little marbles like we want to imagine. They behave like probability waves that can interfere with one another or even themselves, which is how we end up with such a weird-looking interference pattern on the other side. Personally, this visual here helps me feel a little bit better about the interpretation of the object somehow passing through both holes at once. Because if we picture them as waves, and if we picture them instead as a wave source with the waves expanding outwards, it becomes much more believable, at least in my brain. Now, the interference pattern clearly shows both constructive and destructive interference. Constructive interference happens when the wave functions combine and amplify. That's how we get these peaks. It increases the probability of finding a particle at that location. Destructive interference is the exact opposite. That happens when wave functions overlap in opposite phases, reducing or even completely nullifying the probability of detecting the particle in that space, and that's where these troughs occur. And remember, remarkably, this interference pattern emerges even if particles pass through one at a time, underscoring the quantum nature. Each particle is actually able to interfere with itself. So in summary here, superposition is not just a mathematics trick. It's a real physical state where the particle isn't in one place or the other, but kind of both at once until measured. It proves that quantum systems behave fundamentally differently from classical ones. And it also plays a crucial role in quantum algorithms, as we'll see later on. It allows quantum algorithms to amplify the probability of correct answers and cancel out the wrong ones through careful manipulation of quantum states. All right, we're done with that short interlude for now. Let's rejoin our quantum timeline. Now it is 1935, and time for the publication of one of the most influential papers in physics of all time, the EPR paper, named for Einstein and his colleagues Podolsky and Rosen. Its full title is can quantum mechanical descriptions of physical reality be considered complete? Question mark. The EPR paper challenges the completeness of quantum mechanics, but not its correctness. Here's the gist. Quantum mechanics predicts that two particles can become correlated in such a way that measuring one instantly determines the state of the other, even if they're really, really far apart. We now call this entanglement, but Einstein at the time famously called it spooky action at a distance. This suggested that either information is somehow traveling faster than light in between the two particles, which violates special relativity, which says nothing can travel faster than the speed of light, or the particles had pre-existing properties, and he called them hidden variables that quantum mechanics didn't account for. Therefore, the EPR authors concluded quantum mechanics must be incomplete. There must be some deeper theory that restores local realism, the idea that physical properties exist independently of observation and that nothing is influencing anything else faster than the speed of light. In response, Erwin Schrödinger wrote a paper agreeing with Einstein that quantum theory implied something very strange. And in it, he coined the term entanglement, or in German, I'll do my best to pronounce this, Verstrickung, meaning something like intertwining or linking together. He declared that entanglement was the core mystery of quantum mechanics. And the significance of all of this was that we finally recognized that entangled systems behave as a single quantum object, no matter how far apart their individual components were. And you'll note here, unlike on every other slide, I don't have an image to show you because personally, I hate all visual representations that people have come up with in order to show entanglement. And yes, I'm being a little silly, I'm being a little tongue-in-cheek here, but anything that I could show you would in some ways be false or at least misleading. And that's why so many people hated and still don't like the idea of quantum mechanics, including Einstein. And that's why so many people try to argue with me and my colleagues online or in YouTube comments. To some, it is just very unsettling that there's not an accurate picture that you can visualize for what's going on. And there's no good metaphor that accurately describes it either. I guess once you get to the point in your career, or you've just been studying it for quite a while like we have, you kind of just get over that. I'm sorry that's not more satisfying, but it remains very cool nonetheless, and also extremely useful. Now, a few months later, Schrödinger responded to the EPR paper. Schrödinger proposes the idea of Schrödinger's cat, a thought experiment to illustrate the bizarre consequence of superposition and entanglement. In 1936, follow-up discussions were had where Schrödinger continued to explore entangled systems. Schrödinger agreed what EPR described was weird, but he disagreed that it meant that quantum mechanics was wrong and incomplete. Instead, he thought it revealed something fundamental about quantum systems. It was so profound because entanglement meant that quantum reality is inherently non-local. A measurement on one particle can instantly affect the other, even across the world or the universe. Schrödinger realized this was not a side effect or a quirk, it was an essential feature of quantum theory. If we're talking about entangled electrons, for instance, which is what is shown here mathematically, and what has come to be known as a Bell state, we see a state described where neither electron individually is in a definite spin state. The pair together has a perfectly defined relationship where if electron A is measured to be up, electron B will instantly be found to be down. If electron A is measured to be down, electron B will instantly be found to be up. Before measurement, neither electron has a definite spin, only the entangled combination is well defined, kind of like the idea of the cat in the box, where we don't know if it's alive or dead until we open the box and that measurement has been made and that measurement defines the state of the cat. The system as a whole has a definite property, but the individual parts do not. And so psi, x of A, and xb cannot be separated into its individual components. And you can see this in the first equation because no single component here can be factored out of the parentheses. Now, after the intense philosophical debates of the 1930s, EPR, Schrödinger's cat, most physicists stopped kind of worrying about quantum weirdness. Instead, they adopted what we call a shut up and calculate attitude. And this is something that's told to many young physicists in their quantum mechanics classes at some point, one or another. They used quantum mechanics to make precise predictions. They stopped debating its philosophical implications. And really, this approach kind of worked. As a result, there were tremendous advances in understanding atoms, nuclei, and fundamental forces. For instance, QED was invented, quantum electrodynamics, and it's the quantum field theory that describes how light or photons interacts with matter, charged particles like electrons and positrons. It's one of the most successful and precisely tested theories in all of physics and science. Richard Feynman introduced Feynman diagrams, as shown here, a visual shorthand for calculating interactions in QED, now standard across particle physics. At its core, QED says that charged particles emit and absorb photons, which are the force carriers of the electromagnetic interaction. These processes are probabilistic and governed by amplitudes, not certainties. And lastly, interactions can be calculated using these Feynman diagrams, each representing a possible path particles can take. And like I said, QED is one of the most accurately tested theories in physics. For example, the anomalous magnetic moment of the electron, a small deviation from what you would expect classically, has been predicted and measured to an agreement of more than 1 part in a trillion. There are not very many theories of nature that come even close to that. The development of quantum mechanics was also crucial to the advancement of nuclear theory in the 30s and the 40s. Without quantum mechanics, scientists wouldn't have been able to understand how nuclei are structured, how they behave, or how to manipulate them in reactions like fission. We have now arrived in the 1960s. Quantum mechanics has become incredibly successful at predicting experimental results. QED has made astonishingly precise predictions, such as the electron's magnetic moment and the Lamb shift, with experimental agreement to parts per billion. The impact of this was that quantum theory wasn't just weird. It worked better than anything else. Scientists stopped doubting its correctness and focused on using it. To set the baseline, now the question became not whether quantum mechanics is correct, but again, what does quantum mechanics actually say about reality? Physicist John Bell formalized the argument into a testable mathematical inequality called the Bell inequality. It basically stated that if experiments violate Bell's inequality, local hidden variables cannot explain quantum mechanics. And surprise, surprise, this was eventually tested in the laboratory, and when these experiments were done, carefully and correctly, of course, they were all found to violate the inequality. I'll dive more into these details in just a second. But the overall message was this. Bell turned philosophy into experimental physics, which is just so cool. It became possible to test the fundamental nature of reality, and quantum mechanics could be tested against what we might call common sense, local realism, and possibly be shown to violate it. Now let's turn to one of these key results in the foundations of quantum mechanics and the Bell's inequality, the CHSH inequality specifically, named for Clauser, Horn, Shimony, and Holt. This inequality is a testable version of Bell's theorem, and it gives us a way to experimentally decide. The experiment aimed to answer the question, is the world governed by local hidden variables, or does quantum mechanics really allow for non-local correlations? Here's the very basic setup. We have two entangled particles sent to two distant observers, commonly called Alice and Bob. Each can choose between two measurement settings, say A or A prime for Alice or B prime for Bob. This could be measuring different directions or alignments of the particle. But each experiment yields a binary result, either 1 or -1. Now, if the world were governed by local hidden variables, meaning each particle carries pre-programmed instructions and no faster than light influence is occurring, then there's a strict limit on how correlated Alice and Bob's measurements can be. Again, assuming nothing else. The limit is expressed by the CH-SH inequality shown here, where the terms E of A and B are the quantum correlations of the particle pairs, where the quantum correlation is defined to be the expectation value of the product of the outcomes of the experiment. This value must be less than or equal to 2, assuming nothing else, just locality and realism are the only things in play. But here's the kicker. Quantum mechanics predicts violations of this inequality. It actually predicted that we will measure not 2 or less, but 2 square root 2, which is about 2.8, obviously higher than 2. This is beyond anything any local theory could produce, and it's been confirmed in dozens of experiments, including loophole-free tests in recent years. So what does this mean? It means that nature doesn't obey local realism. There are no hidden variables that determine outcomes in advance while keeping everything local. Instead, entangled pairs are deeply connected in a way that defies classical explanation. And yet, they still don't allow faster than light signaling. And this isn't just a philosophical result. These non-local correlations are now resources in quantum cryptography, quantum networks, and even device-independent quantum computing. The CH-SH inequality draws a line in the sand, and quantum mechanics steps over it. And actually, you're going to have a chance to do just the same in the first lab assignment of the summer school. It's really cool, and the fact that you can do these kind of experiments now, just from your home with Qiskit, it blows my mind a little bit. And if you're interested in learning more about Bell's tests and Bell's theorem and how the Nobel Prize in Physics was awarded just a few years ago for demonstrating these results, I encourage you to take a look at one of my other videos on the channel called Bell's Inequality, the weirdest theorem in the world. And this actually brings me almost to the end of what I wanted to cover in today's lecture. But before we end, let's now briefly talk about the birth of quantum information science, a pivotal shift that began in the 1990s. This is the era when researchers stopped asking, why is quantum physics so weird? And started asking, how can we use that weirdness for something useful? In 1994, Peter Shor and Love Grover proposed groundbreaking quantum algorithms. Shor's for factoring large numbers exponentially faster than classical computers, and Grover for searching through unsorted databases quadratically faster. And these weren't just theoretical curiosities. They revealed that quantum mechanics could be computationally useful. And then in 1996, David DiVincenzo clearly laid out a set of criteria that any physical system would need to satisfy in order to serve as a quantum computer, one capable of actually running Shor and Grover's algorithm. It talked about initializing qubits to implementing gate operations and then error correction. Around the same time, experimentalists were making early progress towards realizing qubits in the lab, using systems like trapped ions and superconducting qubits. So what was the impact of all of this? A mindset shift. Scientists began to see that quantum weirdness was not a bug, it's a feature. Instead of resisting entanglement, superposition, uncertainty, they started engineering around them, laying the foundations for the quantum technologies that we're building today. And like Newton once said, If I have seen further, it is by standing on the shoulders of giants. And us working in the field of quantum information are indeed standing on the shoulders of some of the most important and impactful scientific giants to ever live. This field directly builds on centuries of physics, and the 1990s marked the moment where we began to harness those ideas, not just to describe the universe, but to compute with it and understand it even better. And now it's your turn. And here's the best part. The story is not finished. It's still being written in code, in labs, in theory, and in lectures and stories like this one. The next Shore or Grover might be turning into the summer school right now. I hope they are. All right, so now we're really at the end here. If you weren't familiar with this long history of quantum mechanics and quantum physics, and surely I missed some things and I didn't touch upon every single experiment, I hope you at least enjoyed some of this walkthrough about some of the major discoveries that happened in the past century. And if you were already familiar with most of this, I hope you still enjoyed reminiscing and pausing to gain a bird's eye view of how far we've come. And I know I did. Thanks for watching, and make sure you tune in tomorrow for the next lecture of the 2025 Qiskit Global Summer School. Thanks.
People weren't exploring already, and then just to like stay on top of the literature because everything in this field moves so freaking fast. So that's, I think, the hard part, not the beginning part. So that's, I think, a pretty common misconception. And then one thing that I wish people asked me, which they don't ask me so much, this is a broad answer and it's non-specific, but I think one thing I wish in general people understood is that this is obviously also a networking opportunity. And we do a lot of networking opportunities at IBM. And in general, I think it's a really good idea. But you should be networking with people before you're looking for a job and an internship. So, one common mistake that I wish people would stop making is trying to connect with me or a colleague when you have like a specific request, like, hi, I need a job tomorrow. That's not great networking. Good networking should happen months to years before you're looking for a specific opportunity. And when you're just looking for general mentorship and you're looking to connect with somebody and learn from somebody just for like the sake of learning or for the sake of like building a relationship. So if you're just like reaching out to people in the field to try to get something specific for them, it usually isn't going to work out in your favor.
Completely agreed. And that also leads into our next question, which is next steps after successfully completing QGSS 2025. And I know we'll talk more about that as we near towards the end, but would love your
Yeah,
take
we're
on
going
this,
to talk
Olivia.
about a lot of cool next steps for you. I think, if you had a good time, obviously apply for an internship next year, depending on like your geographic location. If you're a student, consider joining the quantum computing club or starting a quantum computing club at your school. We've had a lot of people graduate from the school and decide like, my school doesn't have these opportunities. I'm going to make them myself. And that's always extremely rewarding to see. And those people do extremely well, I would say, in their career in the long term because they build up this intuition and skill set about like managing a club and also just like starting something off on their own as well. So I super encourage that. There's a lot of independent learning you can do on the IBM Quantum Learning platform, which I certainly encourage. There's some more advanced stuff there too. If you've just sort of like whet your appetite and you're like, I'm looking to get more involved in something technical in this path, go check out those courses. And then videos as well on the Qiskit YouTube, like since Grady already said. I think the Qiskit YouTube is a great learning place. It depends where you want to go. I'm sorry, I keep saying it depends, but it's true.
Awesome. And Our next question is about cybersecurity. I've learned that quantum computing poses a great threat to current information security infrastructures. What are possible measures to mitigate this threat? And is it possible to come up with a classical algorithm that a quantum computer cannot solve in polynomial time? So I guess that's sort of two parts.
Yeah, so that's certainly true. Quantum computing could pose a threat to traditional security on computers. But luckily, IBM has been working with the National Science Foundation and a lot of other government entities and companies as well to come up with some quantum safe algorithms, which we are working to implement broadly over the next few years. So we have a plan. We know that this sort of D-Day of encryption, or Q-Day, some people call it, is coming, but we have ways to combat that. And we have algorithms that we have already invented, that IBM has invented, actually, that we just need to encourage others to implement. And, on a pretty fast timeline, I would say. We're working with the government to try to do that as quickly as possible.
Awesome. Now, what would you say to people who say quantum computing is all hype?
Um, I would say I understand why they feel that way, and the field has not done the best job of science communication. I would say, especially in the past 5 years or so, there's a lot of places where I think we have fallen short. So I understand why people would think it's just hype. But I would say, if you look at the actual scientific progress that's being made, the literature that's coming out, which is not as accessible as marketing blogs. So a lot of people don't do that and don't get to see it. But if you look at like the scientific papers being published that are on like the archive or in scientific journals, and you also look at roadmaps from major companies like IBM, but there are others as well, and you keep track of how well they fulfill their promises, then I think you'll see that it's not all hype. Like, we would not be putting this much effort into something and checking off those boxes that we promise consistently every single year if it was just hype.
Awesome. And then the next question is, um, do you or IBM work with companies on real use cases? If yes, could you share some of them?
Sorry, what was the last part you just said really quickly, Secretary?
Oh, yes. If yes, could you share some of those use cases?
Oh, sure. Use cases. So one of the ones I'm really interested in are chemistry, materials research. I think those are sort of like near-term applications. There's some cool work that we're doing with companies like Boeing to explore materials and try and come up with different optimizations of alignment in material structure. Batteries are a really good example. And then there's also optimization in finance, which I think is really cool. I'm not as familiar with finance. I'm not a finance person. But I think the idea of like portfolio optimization and fraud detection in finance, which quantum computers could be really good at, is very interesting. So those are just some of my favorites, but there's so many.
Agreed. And then have there been moments when your outreach efforts discovered new research questions or collaborators?
Collaborators for sure. So yeah, I guess in that way we have come up with new research questions. We've had some really good collaborators that we have discovered from people basically using IBM systems. But like, we would see the paper and we would think like, oh, well, that's a really interesting technique. I wonder if they thought of trying, this additional method, or maybe they started going down this path, but we would recommend this path instead. So we have found collaborators that way, and we have been able to answer some interesting research questions and basically explore new topics that we wouldn't have just by ourselves, which I think is really the point of what we're doing and science in general. Like, we don't want to only be the sole providers and gatekeepers of knowledge. We want as many people involved as possible.
Awesome. Now switching into technical questions, what might the results of a triple slit experiment be? Quadruple slit?
Oh, yeah. If you had a triple slit experiment, you would just see a different type of interference pattern. It would just look like different squiggles, depending on like the size of the slits and how close they are together. That's actually probably more important for like the type of pattern you would see than like how many there are. They've done multiple triple, quadruple slit experiments. It doesn't really matter how many they are. The underlying principles are still the same. Yep.
Awesome. And then have there been any advancements in the philosophical implications of the development of quantum mechanics?
Yeah, I think so. I think one of the more interesting things that we're going to learn in the next few years is in the philosophical realm umbrella. One of the things that I explored in graduate school that I would say was experimental but also philosophical was the idea of weak measurement. And again, I just like measurement. I think it's really cool. But what we're used to when we talk about measurement in quantum mechanics is strong measurement or projective measurement, which is a total collapse of the wave function into a classical state. But a weak measurement is basically like when you measure something a little bit and you learn a little bit of information instead of like all the information. So I didn't know that that was possible. And the fact that you can do it not just theoretically, mathematically, but you can do it in a lab to a qubit, I think has some interesting philosophical implications. Like, what does it mean to measure something a little bit? So, I mean, there haven't been like any grand results. Like, we haven't solved the measurement problem. We don't know what the collapse of the wave function actually really means yet. But we have learned some things, and I think we'll learn more.
Awesome. And then this next question is about measurement. The measurement problem remains one of the most fundamental open questions in quantum mechanics. If this problem is someday resolved and we succeed in discovering the exact mechanism behind collapse, or develop new mathematical tools that allow us to predict which state a particle will collapse into, does that mean superposition was never truly physical, just a mathematical artifact? And two, the entire probabilistic nature of quantum mechanics would break down since we no longer need probabilities to describe outcomes.
So we know we need probabilities to describe outcomes. We know that part is true. We don't know the underlying mechanism that I guess can make you picture what entanglement is, but we know it's probabilistic. So that part isn't going anywhere. So I don't think it's quite as negative as maybe you explained in the second half of your sentence. But I do think it's possible that one day we'll learn more and we'll have more of a conceptual understanding. I just don't think it's going to change the underlying mathematical structure because we know that that mathematical structure and how we conduct experiments using it is the most accurate and predictive scientific method that exists. So I don't think that's going anywhere.
That's good to know. And then we have a couple questions about observables. If you could explain them again and how estimators impact them.
Yeah, so an observable is just something that you can measure in a quantum experiment. So the most classic examples are like position and momentum, but you can also measure phase. You can measure, the state of a qubit. These are observables. Not everything can be measured, and certainly not everything can be measured simultaneously. So when we talk about expectation values, we also talk about which types of observables can be measured at the same time. Like phase can be measured at the same time as some of the other ones I mentioned, but you can't measure position and momentum at the same time precisely. That's where we get the uncertainty principle from. I hope that answers
Awesome.
it.
No, that's a really good explanation of it. And then how many particles in nature are already entangled and how did they get that way?
Oh, I have no idea. I don't think oh, that's a good question. I have no idea how many particles in nature are entangled. I'm not sure if there are any. Uh, Probably there are, but you can create entanglement from a wide variety of mechanisms. So I don't know how you would tally that. Sorry.
Um, yeah, I guess we should go out and start counting now if someone hasn't already. But to switch frames a little bit, going into a group of questions people are having about is it too late to start quantum computing if I am already in like established field? Is it too early to start quantum computing if I'm a beginner? Do I need a PhD?
Yeah.
Um, what is your take on that?
I mean, I don't think it's ever too late to learn anything. If you're, looking for a job in the field and you're 1 year away from retirement, I might be like, why? But I don't think it's ever too late to learn anything new. Um, some people might say, like, is it too early? And I could see that argument being made. Like, I do see high schoolers asking us for internships a lot, and we don't accept high schoolers. It's a little too early for you, just because of the law, to like actually dive into a career in it. But that doesn't mean you can't learn independently and get started and build up your fundamentals if you think it's interesting. I don't think it's necessary. And I think no matter where you are in your career, like I said, unless you're like a year from retirement, it's not too late. It's never too late to change career paths if you find something more interesting. So no, I don't think there's like a definite timeline that you have to follow.
Awesome. And then do you think people need to get a PhD to get
Yes,
involved?
that was the other part of the question. No, I don't think so. You don't have a PhD, right? Not
I
yet, since
don't have a
green.
PhD, no, not
So
yet.
look, she's here. She's doing great. Yeah, you don't need a PhD. It depends what you want to do. If you want to be like, a leading researcher in error correction, I'd be like, yeah, you kind of need a PhD for that role. But there are plenty of roles that don't require PhDs for sure.
Exactly. And for context, I'm a product marketing manager, and there's roles across the stack from the business side to the software side. So don't necessarily need a PhD if you don't want to get one right away. And then the next questions are sort of around what is the current state of quantum computing and what can we expect in the next 5 to 10 years?
Yeah. So in the next 5 years, I think what we're really looking for is that those experiments that prove quantum advantage. And I'm using the term proof loosely here because I think when quantum advantage results first start emerging, it's going to take a while to verify them. Because one of the things we have to do is sort of wait and see how classical methods are going to respond, because it is sort of, a race where one is overtaking the other and then back and forth. But that's to be expected. I think that that's what's going to happen in the near term, like 5 years. And then if you look to 10 years and further than that, the important things that we're going to see are like fault tolerance quantum computers and universal quantum computers emerging. IBM has a plan to do that up in our Poughkeepsie lab in New York in 2029. So you can read a little bit more about that on our blog if you're curious. And then after that, I would think that quantum solutions would become ubiquitous. Whether people working in technology or industry know they're using quantum solutions, I'm not sure, because I think part of the interesting way that we're going about things is that we are creating supercomputing infrastructures that will be designating jobs to both classical supercomputers and quantum computers. So it sort of will just give the workload to the type of computer that is good at solving that type of problem. But I think, in the next 10 years, this becomes pretty commonplace.
That's so exciting. And I feel like those advancements are happening across the stack, hardware and software. So there's a place for everyone to contribute. So with that, we're at time. One last question for you, Olivia, before we let you go is what is one lecture or lab that you're really looking forward to for Qiskit Global Summer School?
Um, so one thing that I'm really looking forward to is Patrick Rawls' lecture. I think it's next week. So you're gonna have to stick around for a while. Patrick is just such a good lecturer. I've learned a lot from him recently. I've been working with him a little bit to understand more QEC stuff. He's a pure theorist, and I'm really pure experimental from my background anyway. So I've learned a ton from him, and he's a really masterful lecturer, and I think you'll really enjoy that one.
Awesome. Well, thank you so much for being with us today, Olivia, and thank you to you all for asking all of these amazing questions. Keep that excitement and enthusiasm with you as we go throughout Qiskit Global Summer School. And yeah, thank you guys.
Thank you guys so much.
And one.
So, hello everyone, and welcome everyone to the first lab of Qiskit Global Summer School 2025. So, I will start sharing my screen and let's start our lab one walkthrough session. Is it time? Okay, this one. Okay, so everybody can see my screen now? Okay. It is not a recorded video. So, so let's start the lab one walkthrough session now. So this lab is about recreating very historical experiment mentioned in Olivia's lecture. So the title of this lab is Recreating Famous Experiment at Home. And our goal is to explore four fundamental concepts of quantum mechanics by working through three famous experiments. By the end of this session, we'll be comfortable composing quantum circuits with single and two qubit gates and running them on both simulators and real quantum hardware. More important, you'll get hands-on practice with the entire Qiskit pattern framework. This is four-step pattern you will see again and again at this lab. So first, you map a problem to a quantum circuit. Second, you optimize the circuit for your target hardware. Third, you execute it. And finally, you post-process the result. So please keep in mind that all exercises in this lab follow this four-step closely. So let me introduce who put this all together. So this lab was created by a great team here at IBM Quantum Education team, myself and my colleague Jim Weaver. For those who don't know me, I'm Soyoung, a quantum strategist at IBM. I hold a PhD in physics from Southwestern University and transitioned from atomic physics to quantum computing after the 2020 IBM Quantum Challenge. At IBM, I create educational content and work closely with our partners in North America. What I love most is mentoring students, and I'm truly honored to be a career mentoring fellow of American Physics Society. My awesome colleague James Weaver, is a developer, author, and speaker with a passion for quantum computing and AI. He is a Java champion and a Java 1 rockstar. James has written several books, including Inside Java, Beginning J2EE, the Pro Java FX series, and Java with Raspberry Pi, and the famous Qiskit book like Qiskit Pocket Guide. As an IBM quantum developer advocate, James speaks internationally about quantum computing with Qiskit and AI at quantum and classical computing conferences. And of course, this lab was a true team effort. I want to give a special thanks to our advisors, Marcel, Jesse, Junie, and Borja, for their critical technical guidance. I also want to thanks to our reviewers, Meltem, Evie, whose feedback on the content was invaluable. So my goal today is not give you all answers, but to walk you through the core concept and provide the key hint you'll need to confidently solve the exercises in your own notebook. So before we dive into exercises, here a quick overview of Lab 1. The difficulty level is for beginners. Through Olivia's lecture, you already have some basic theory and historical background. This lab notebook also provides plenty of details of each experiment, including the mathematical equation and formulas. So if you ever get stuck, be sure to take a closer look at those explanations. And I also want to point you to a few other amazing resources that will bring a huge help. First, John Watrous' Basic of Quantum Information course. So the first few lectures are a great companion for the exercises in Chapter 1, and the final lecture will be crucial for Chapter 2. And as a bonus, you can earn a foundation level badges for completing this course. Second, the Circuit Composer. So if you are new to Qiskit, this is a great visual playground for testing ideas before you code. You can drag and drop quantum gate like this. You can remove as well. And here you can simultaneously see what happens at your qubit state just by adding your quantum gate here. A more fantastic feature is that you can run your circuit on a real hardware directly from this composer with just click. Also, I wanted to highlight a work of our key community members. So Diego. So for your information, he is also a mentor of this event. So Diego is a Qiskit advocate who has contributed to Qiskit textbook and SDK and several repositories. And for this lab specifically, I highly recommend his YouTube series, The Quantum Double Slit Experiment and Mapping the Double Slit Experiment onto a Quantum Circuit. It provides a fantastic step-by-step guide. So, all right. So with our essential libraries imported and runtime setting complete, let's dive into the lab. So first, exercise 1. So exercise 1 and 2 is about double slit experiment. So for the exercise 1-1, the goal is to make our qubit pass through both slits at once. So what's the fundamental gate we use to create a perfect equal superposition from an initial zero state? That's exactly the gate you need to apply here. And exercise 1-2 will model the screen where the path from two slits interfere. The trick here is to apply the same gate again right before you measure. So this is what creates that class constructive interference pattern at the center of the screen. And a quick but important heads up for this first two parts is the code for lab exercise 1-2 adds gate to the circuit from 1-1. So if you run the code cell multiple times, we'll keep adding more gates to the circuit, which will mess up your result for the grader. So just be careful to run it only once per attempt. And now let's go to the exercise 1-3 and 1-4. So the exercise 1-3 and 1-4, we will introduce a phase difference to see what happens at the other point of the screen. So at 1-3, your job is to apply a phase between two superpositioned gates. Look for the Qiskit gate that does exactly that, like apply a phase shift only to one of the paths, like one state. Then in 1-4, we'll make a phase, a variable to generate the full interference pattern. The key here is to use Qiskit parameter in your circuit. The lab provides the rest of the code to run parameterized circuit and generate the beautiful fringe like this. So if you code well, you will see this beautiful fringe pattern at your exercise 1. And before we move on, I want you to notice the key difference between this experiment like exercise 1 and exercise 2. So it's about how we control the final outcome, really. So in the double slit experiment, it is all about interference. So we first create a superposition, and then we introduce the phase difference between passes. That phase is what controls the interference and ultimately the final probabilities. In contrast, the Schrödinger cat exercise 2 is about direct rotation. So we are going to use an Rx gate to directly change the probability amplitude themselves and controlling how much happy cat versus unhappy cat we have. So think of it way, interference versus direct rotation. So try to catch this conceptual difference as you walk through the next two exercises. So now let's move to exercise 2, the Schrödinger's cat. This exercise is a fantastic way to understand the role of measurement and probability. Your main tool here is the rotational gate. But think of its angle, theta, as a dial that controls the cat's fate. Here, not a dead or alive, but happy or unhappy. So if the theta is 0, the cat is happy. And if the theta is pi, the cat is fully grumpy. So any angle in between, put in a superposition, directly control the final probability. And pay close attention to the fact that we use only shot equal 1 here. here. And this is crucial because it mimics the single act of opening the box to see the one defined result. And please remember, you need to put two cat images at the same folder with the lab notebook to guarantee this widget work properly. So if you code well, you will see this nice widget over opening the box to see if the cat is happy or grumpy. And finally, the end of chapter 1 exercise 3. So exercise 3 brilliantly bring both of these ideas together. So we are going back to double slit experiment, but this time we are adding ridge path detector. The key technique here is mid-circuit measurement. So yeah, mid-circuit measurement. So we will place a measurement right after the first superposition gate, but before the second one. And this acts as your detector, forcing the qubit to decide which path it took. So what should you expect to happen? So as soon as you add the measurement, the observers, the beautiful interference pattern will completely vanish. So we will see the observer effect in action. We're gaining information about paths destroyed, very superposition, and what's necessary for the interference to occur. So this is the end of chapter 1, and next, Jim will give you a walkthrough for chapter 2.
Hi, thank you, Sophie. So I see on the chat that there's some lagging going on. And so I'm going to ask questions just to make sure that everybody can hear me. First of all, the next exercise has to do with the CHSH game. Has anybody heard of the CHSH game before? Please answer in the chat so that I know. I see a no. How about a yes? Oh, there's a couple of yeses. Somebody want to tell me about the CHSH game? I will go ahead and describe it. But what it is it's a thought experiment. It's a kind of a fictitious game in which we use an entangled quantum resource to beat the odds, to play a game better than we can and win more than we can classically. And so it's an experiment that demonstrates entanglement as a resource. And so this notebook, then you will go through and explore that and play with rotation angles such that you achieve better than classical odds. Okay, and there's still a lag. Does anybody need me to repeat any of that, or are you good before we go on to the next one? I love the comments in the chat about the poor kitties, by the way. That was pretty cool. Okay, so the next one then is quantum teleportation. That's another case that we use quantum entanglement as a resource. And so here we are then teleporting a quantum state from Alice to Bob. And we're not actually, teleporting the particle itself, but we are teleporting the state so that then Alice can set up a quantum state and then Bob can receive it. And so this explores that classic teleportation experiment. And so you should be good to go there. You just follow through the instructions and fill in code. Any questions?
Okay, then maybe it's time to just introduce the last extra open challenge, right?
Yes.
So, and at the end of this lab, for those who are ready to have a deeper challenge, we have a special bonus challenge like taking this teleportation happen between physically disconnected qubit by using IBM's real hardware. So on a real chip, you can only perform two qubit gate like C NOT between qubits that are physically next to each other. So to connect to distant qubits, you need a series of swap gates to move one qubit state across the chip until they become neighbor. And this each swap gate adds depth and complexity to your circuit, making it more vulnerable to noise and errors. And this is where the dynamic circuit becomes so powerful, helping manage this complexity in real time. So your mission here is how far can you faithfully teleport a quantum state physically? So try to pick two qubits that are not directly connected, run the teleportation protocol, and measure the fidelity. And here we will provide a supplemental notebook, which will be provided you separately. An abstracted version of IBM's long-range entanglement tutorial has all the code you need. So this file will get the same GitHub repository, and you can download it and you can try this. So the kit technology, the supplemental notebook, which will be provided to you, is about providing three key functions. So you can just use instead of just a CNOT CX gate. And the key steps are connecting to the runtime service, picking up backend, and then studying its coupling map to find your distant qubit and plan your route. And this is a tough but very rewarding. So if you have time after finishing 11, just try to take a look at this and try to explore the latest dynamic challenge with this extra lab. So this is the end of our lab 1 walkthrough. So good luck, everyone, and be sure to share your achievement with folks to encourage each other and inspire each other.
Have fun.
Yep, have fun. Thank you.